For this lab, you'll need a track, pulley, cart, string, spring gauge, a hanger, and an additional mass. Masses, or what everyone else calls weight, masses will have their mass printed or imprinted on the base. Over on the right, hopefully we can see this, there's a 50G, meaning it's 50 grams. Our mass over to the left here also has a mass of 50 grams. Other larger masses that we'll be using to add to the cart will be, let's say, this 500 gram, which is half a kilogram mass, and then maybe this round one, you can see here where it lists 500, again another 500 grams. We'll use a combination of weights, like this, to provide different tensions on the string that we'll use to pull our cart. To measure the weight, you'll have to do this a couple times for each configuration. Hey, I'll take my spring gauge here. Support the weight and read the force off the gauge. It isn't all that clear, but when you're doing this for real, you'll see that the side you want to read says N for newtons. And you look at where the top of the plunger is compared to the dial. In this case, it's reading just about, let's get a better picture of it. Getting it? It reads just about 1 newton. Make sure you don't read the other side, which ends up listing things in grams. Read the newton side. Cut a length of string so that you can put a loop on it on each end, and it just about reaches the floor. All right. I've just got this larger mass just to hold it in place. Your full setup will look something like this. I have my mass hanging from the string, providing tension, attached to the cart. The cart, notice I have extra masses on top of that to help slow it down. So it's somewhere between 1 and 2 kilograms on top of that will work out well. The round mass that's sitting on the track is just to keep the thing from moving. And then I have my motion detector behind that set up to capture motion. So for the lab, start the Logger Pro, acquire data, go ahead and release the cart, allow it to start moving, catch before it hits the end. Okay. As the weight falls. Let it rest there. There. Don't let it run into the end or it'll end up breaking the cart and the pulley. As you started your Logger Pro acquisition before you release the cart, you'll have a period of 0 velocity. Then the cart will start moving. In this particular graph, starting at 1.2 seconds. We want to allow the cart to move for at least 2 seconds. It could be more than that, but at least 2 seconds. You can see here at the end of the 2 seconds of motion, it ends up having some final velocity. You do this once for the light weight, another time for the heavier weight. The recommendation is you do it for the heavy weight first because the drop time will obviously be less, and you use the same drop time for both the heavy and the light weights. Using the Logger Pro software, we record the velocity of the cart as it moves. Notice here from 0 to about 0.8 seconds the cart was held still, then it was released, gradually speeding up to a maximum speed of about 0.8 meters per second. Then it was caught and the velocity dropped back down to 0. We're going to start filling in our table. A few things have already been filled out. This is the heavier hanging mass. It was about 100 grams, so I've changed my unit from kilograms to grams. The cart mass, the cart itself has a mass of about 0.5 kilograms and piled a lot of other stuff on top of it. So it had a mass of about 3 kilograms. That's at the beginning and at the end. And then just using the spring scale weighed that 100 gram mass that was hanging off over here, hanging off the end of the string, and found out that the tension was about 1 newton. We're going to use the, our plotted data here to fill in the rest of this table. So I'll use the time at 0.8 seconds here as our starting point, and the velocity there was 0 meters per second. Now it looks like we got from about 0.8 to just about 3.2 seconds of good linear data. So the change in time from 0.8 to 3.2, our time there is 2.4 seconds. And at that very end right up here, we're looking at a velocity of about 0.8 meters per second. So I'll just write it over here. 0.8, you can see the meters per second are listed here. Now I'm going to compute my products with units. 3 kilograms times 0 meters per second, I'll get 0. And if we take a look at our units, kilogram meter per second, we recognize that as the unit for momentum, which fits in because we have a cart mass of 3 kilograms, a velocity of 0 meters per second. Mass times velocity is, in fact, our momentum. Let's take a look at this next one. 1 Newton times 2.4 seconds. 2.4 times 1, I get a value of 2.4 Newton seconds. This can also be expressed as 2.4 kilogram meters per second. This is the impulse, which is also our change of momentum. At the end, let's take a look at here. I have a cart that's again at 3 kilograms times 0.8 meters per second. 3 times 0.8. Wow, that worked out pretty well. I get 2.4 kilogram meters per second. Experiment came out pretty well. Yours, we'll see how we do. But it makes sense that our initial momentum plus our impulse, which causes a change in momentum, is equal to our final impulse. Hey, so I made a couple of sketches. I got started. My initial sketch is the car standing still with the mass hanging here. The force on the cart and its direction. Hey, we're going to have we think of that tension is going to be pulling to the right. So we have a force of tension to the right, and that's going to be 1 Newton. Okay, and our final sketch, I'll make a quick sketch here. We're just about at the end. We're at our maximum velocity. The hanger is way down here. The car is moving along pretty quickly. Here at the initial condition, our initial velocity is equal to 0. If I look at the graph, I can see my final velocity here is 0.8 seconds. Hey, just to emphasize, how did I get a time of 2.4 seconds? I'm just looking with the heavier weight, how much kind of linear change can I get before I have to stop this thing. Let's go ahead and we're going to plot our mass and our velocity on a velocity versus mass graph. Well, my velocity is 0 and my mass, if I put this as being 1, 2, 3 kilograms, I really have almost nothing here because I have 0 velocity. Let's come over here, our force on the cart, force, and we have our time, a force of 1 Newton for 1, 2, this is out to 3, about 2.4 seconds. So this area here represents our impulse, or another way of saying it is our change of momentum. Hey, in our final, we're at 0.8. Oh, what did I do here? This is supposed to be, of course, meters per second, not seconds. All right, I'm at 0.5, about this high, and then our mass did not change. 1, 2, 2.4. So we have another way of expressing this. Hey, so we have a 0 momentum plus our impulse, our change of momentum is equal to our final momentum. Let's go and put these in terms. Our initial momentum is 0 kilogram meters per second. Our impulse, we see it up there, 2.4 Newton seconds. Remember, that's the same as a kilogram meter per second. And my final momentum I can see here is 3 kilograms times 0.8 meters per second is 2.4 kilogram meters per second. Remember, these are just some values I was doing in my lab. Your values will be slightly different than these. Okay, I'm going to advance to the next slide. Can I get there? Yes. Okay. Hey, and this is with the lighter hanging weight. And we acquired our data. held it till about 0.4 seconds. But remember now what we still want to have is the same amount of time. So I'm going to set that, list it right here, 2.4 seconds. So if I'm right here at what is this? 0.4 seconds plus 2.4 means that we're going to be out at 2.8 seconds is where we're going to be considering our final velocity. All right, so an important point there, I want to have the same amount of time that I'm speeding up with the lighter hanging weight as I did with the heavier weight. I might start at a slightly different time, but our change in time, our delta x, should still be 2.4 seconds from when we first start moving. Okay, so based off the graph and some measurements, let me go and fill out table 3. Hey, my cart has the same mass. I use the same cart, so 3 kilograms. This time I had the lighter hanging mass. It was only 50 grams. The cart mass doesn't change. Hopefully nothing falls off of it, but 3 kilograms at the end. I went to the spring scale, weighed this, and I found out that my 50-gram mass weighed 0.5 newtons. You'll be able to put that in where the insert characters are or draw it on a separate paper. All right. Hey, so let's go and figure out our initial velocity. Right at this point where it first started moving, we're at a velocity of 0 meters per second. 2.4 seconds later, and velocity is about 0.4. 0.4 meters per second. Hope you can read that. 0.4 meters per second. All right, let's do a little math. The product of mass times velocity gives us our momentum. 3 times 0 is 0. Okay, let's look at this next one. Our impulse, 0.5 newtons times 2.4 seconds is 1.2 Newton seconds. Remember that's the same unit as, let's see, 1.2 kilogram meters per second. Let me put that decimal point in there a little bit darker so you can see it. Hey, now in mind, 3 times 0.4 meters per second, 3 kilograms times 0.4 meters per second is 1.2 kilogram meters per second. We'll go ahead and put these sketches together. I'm going to pause it for a moment and draw up my sketches. Hey, so welcome back. I've put in an initial sketch. My initial velocity is 0. We can see the cart here with the string, and we have the hanger mass. The force on the cart is to the right. We have a tension force of 0.5 newtons. And then our final sketch, we can see with my little racing lines here that the cart is moving to the right after 2.4 seconds at 0.4 meters per second. And the hanger is a little bit lower. Obviously, in this situation, because we don't have as much weight, it won't speed up as quickly, so it won't cover as much distance. Let's go ahead and we'll put our velocity versus mass graph together to start off with. It's going to be kind of boring, but our mass in kilograms, I don't know if I did that on the last one, 1, 2, we're out at 3 kilograms, but we have the just 0 meters per second. So we don't really have, we have a flat rectangle. All right. Hey, so next we have a force of, what's our force here? 0.5 newtons. And for the time, 2.4 seconds. 1, 2, 3. We're going to be out over here someplace. Hey, hopefully you'll notice that this rectangle is not as large as our last one, indicating that the area of this, the impulse, is less than the previous one. Hey, at the end, let's see our mass. 1, 2, 3, again, kilograms. Put seconds over here. All right. Hey, and what was our final velocity? 0.4 meters per second. Just below half a meter per second, all the way out to 3. The area of this graph, velocity times mass, represents the momentum at the end. Let's go ahead and put our numbers here. Our total momentum initial, 3 times 0 is 0 kilogram meters per second. Our impulse, which is our change of momentum, also equal to force times time, is 1.2, 0.5 newtons times 2.4 seconds equals 1.2 newton seconds. We can also express that as a kilogram meter per second. Our final momentum, our measured value, was a velocity of 0.4 meters per second times 0.4 meters per second times our 3 kilograms gives us 1.2 kilogram meters per second. Hey, after you have this table filled out, you'll be in a good position to be able to complete the lab and answer the analytic questions at the end.